All right, so as we take a look at number 4 here, we're going to show by means of molar masses that matter is neither created nor destroyed in the equation given. Again, just a quick illustration of the law of conservation of mass. You're going to need your periodic table to make this happen, but you're going to add together all the masses of the individual elements in each of the molecules here, add them together on the reactant side, and compare them to what you get on the product side. So as we take a look at C2H6O, we would get a molar mass here of 46.068 grams. And again, if you're questioning where that number came from, you just want to go to your periodic table. C2H6O is going to come from 2 carbons, 6 hydrogens, 4, 5, 6, and 1 oxygen. Sum those all together to give us 46.068 grams. You want to do the same thing with your oxygen here, although do be careful because you've got 3 moles of the oxygen gas, so it's going to be 3 times the 32.00 grams for the oxygen, and that should equal, according to the law of conservation of mass, what we've got on the product side. So it's going to be twice the molar mass of the carbon dioxide, 44.01 grams. Plus 3 times the molar mass of water, 18.016 grams. If we sum together everything on our reactant side, we should get 142.07 grams. And if you sum everything on the product side, you'll find that we also get 142.07 grams. Boom, law of conservation of mass. Question number 5, just some quick practice here with balancing chemical equations and things to keep in mind as you balance these chemical equations. First things first, we're going to make a quick list on the reactant side of all of the players here in our chemical equation. We've got sodium, oxygen, hydrogen, and phosphate. Now, as you note here, I broke up the hydroxide polyatomic ion because it doesn't appear on both sides of the equation. But note that I kept the phosphate ion together because it does appear on both sides of the chemical equation, which will make balancing this a little bit easier. Once you've made your list on the left-hand side, you're going to make the exact same list in the exact same order on the product side, which will give us something like this. Then you just want to count up initially how many you have of each of those things on either side. On a reactant side, we've got 1 sodium, 1 oxygen, 4 hydrogen, and 1 phosphate. On the product side, we've got 3 sodium, 1 oxygen, 2 hydrogen, and 1 phosphate. Now again, there's no scientific way to answer this question, it's truly trial and error, but it's important that you start with your metals first. So let's balance the sodium by putting a coefficient of 3 in front of our sodium hydroxide. That'll change this to 3, but it will also affect our oxygen and hydrogen counts. It'll change our oxygen to 3 as well, and turn our hydrogen into 6 on the reactant side. So we have balanced the sodium. Our oxygen, though, is now unbalanced. Hydrogen is unbalanced. Our phosphates are balanced still. So as we take a look at each side of the chemical equation and decide where to balance here, I'm going to come over to my water. I've got 3 oxygen on the left, only 1 on the right. If I put a coefficient of 3 here, that'll change my number of oxygen to 3, and it will also change my total number of hydrogen on the product side to 6. So as we take a look, our sodiums are balanced, our oxygen are balanced, hydrogen are balanced, and our phosphate are balanced. Our coefficients in this balanced chemical equations are 3, 1, although you don't have to write it in, 1, again, not necessary to write in, and 3. Boom, done. Question number 6. We're going to do one more balancing problem here, except it's going to be a combustion reaction. This one we're going to show you a little trick that will hopefully help you balance combustion reaction problems. Same thing here as in the last problem. You want to make a quick list of the elements that you've got on the reactant side, in this case carbon, hydrogen, and oxygen. Again, you want to make that exact same list in the exact same order on the product side. Next, just do a quick count to see how many you've got initially in the unbalanced chemical reaction. We've got 4, 10, and 2 on the reactant side, respectively, for carbon, hydrogen, oxygen. On the product side, we've got 1, 2, and 3 respectively on the product side. As you take a look then, you try to balance this. Remember, you want to save hydrogen and oxygen for last. We don't have any metals here to balance first, so we're going to go to carbon next. We've got 4 carbons on the reactant side, only 1 on the product side. So if I put a 4 here, that'll change my number of carbons to 4. It'll also change my number of oxygens to 9. Next, as we think about whether or not we should balance the hydrogen or the oxygen first, we're going to go to the hydrogen. And the reason why we're going to choose hydrogen is because hydrogen appears only 1 time on either side of the chemical equation, whereas oxygen appears, although only once on the reactant side, it appears twice on the product side. So if you're trying to figure out which one to balance next, go to the one that only appears once on either side, in this case, the hydrogen. We've got 10 hydrogen on the left, 2 hydrogen on the right, which means if we put a coefficient of 5 here, that'll change our number of hydrogen to 10 to balance what we've got on the reactant side. However, it's also going to change our number of oxygen to 13. So carbon, hydrogen are now balanced, oxygen is unbalanced. Here's where we're going to show you a little trick to help you balance a combustion reaction. As you take a look, we've got 13 total oxygen on the product side and only 2 on the reactant side. It doesn't matter what whole number I place here as a coefficient, there's no way I'm going to get 13. So the trick is just use a fractional coefficient to start. So we know that if we could use fractional coefficients, we would use 6.5 because 6.5 times 2 would give us our 13. And that would balance our chemical equation. Okay, and that's great. We've got our chemical equation balanced, although it doesn't show us the lowest whole number ratio between reactants and products. No big deal. We're just going to think about what can we multiply all of our coefficients by to give us whole numbers. In this case, it should be pretty easy to see that if we multiply each of them by 2, this becomes 2, this becomes 13, this becomes 8, and this becomes 10. We've now got our smallest whole number ratio that still gives us a balanced chemical equation, which means that our total number of carbons on the reactant side would now be 8, our total number of hydrogens would now be 20, and our total number of oxygens would now be 26. And that would hold true on our product side as well, except now we've got whole number coefficients to balance our chemical equation.